templates, which actually turn out to still be very useful. And now I can't advance. Thank you. All right. So in Lomets, there's two separate information flows, one that's full chain moving along the top here, and one that's domain specific that become important. So first of all, at the full chain level, we've got our full length multiple sequence alignment. We've used AlphaFold to, among other things, get some contact maps. We can use that in the Lomets meta threading approach to get full length threading templates. And then we feed the distance restraints from those threading templates into DeepFold, which is just an in-house geometry optimization program, to get a full-length model, at least, that's built on the information that we've gathered to that point. And we can search the PDB also to find similar models. That is going to guide the assembly of the domains, which I'll show in a moment. Now, separate from that, we also do our domain decomposition at this stage. I'll talk about the domain decomposition a little bit on the next slide. It's either using threadom or FUPred, depending on your query. But we split the query into domains. For each of them, we're going to make a separate domain level multiple sequence alignment. This is just running DeepMSA2 again on just that domain sequence. We come up with things like distance restraints from that. We go search for appropriate templates, and then we get domain level templates for each of these domains. And we pull these together using the Demo2 programs. This is using this full length information flow to assemble the domain templates together. And then at the end of this, we get two really important sets of outputs. We first of all get these distance maps, both full chain and the domain level, which are going to contribute to the Monte Carlo folding simulations at the end. And second, we get a set of template assemblies that are going to serve as important initial structures for the Monte Carlo. All right, so then just a little bit about domains. We're either using threadom if we've got good threading templates, or FUPred if we don't have good threading templates. These have both been published before. The logic with FUPred in particular is try to find a domain decomposition that maintains sort of compactness of the contact maps that have been predicted based on those early AlphaFold 2 runs. All right, so now we've got all of our domain decomposition, all of our threading done. Now we put the multiple sequence alignments into a set of deep learning predictors to try to get some geometric potentials that we can use in the Monte Carlo simulations. We end up using 3 of these. First is just plain old AlphaFold 2. And this time we're running the full version of AlphaFold 2. Second is deep potential, which is kind of an in-house first generation deep learner. And the third is attention potential, which uses the MSA transformer in the early stages to handle the sequences, and then later on uses an evoformer architecture, kind of like AlphaFold 2. Now, all 3 of these give you contact maps and distance match maps, which contribute to our potentials in the Monte Carlo simulations. Attention potential and deep potential will also give hydrogen bond maps, which also contribute to the folding simulations. And we do get a predicted structure out of this AlphaFold 2 run. And finally, we're at the actual Monte Carlo stage. And so these are very similar to previous generation iTaser replica exchange Monte Carlo simulations. They pull in potentials from the distance maps that we got out of the Lomets threading. They pull all of the geometric potentials we got from the deep learners, and they have the classic iTaser potentials built in as well. We use as starting structures the AlphaFold 2 model that we got here and the full-length Lomets template assemblies that we got over here. Run the simulations, end up clustering, find the centroid of the most occupied cluster, and then we do a little bit of refinement using FGMD and AlphaFold 2 Relax. The refinement doesn't seem to do a whole lot in our hands here, and we end up with our final model. So that is the UMTBM DI-Taser method. I'll also talk briefly about the Zheng group's multi-chain predictions, and then I'll move to Wei for the results. So the Zheng group is built on what we're calling DeepMSA fold multimer, and we're writing this paper up right now. As the name probably implies, DeepMSA2 is going to play a major role here. So the basic way this workflow works is we run DeepMSA2 on all of the single chains. We figure out how to put those MSAs together, and then we use AlphaFold 2 multiper to actually do the structure predictions. So DeepMSA2 is run for each of the unique sequences in this multimer, exactly like I talked about before. Not going to go into it in more detail. So at that point, we need to use those multiple sequence alignments that we get for each of the monomers. And here there are 2 separate important problems to consider. The first is what I'll call MSA pairing. That is, we have up to 10 candidate multiple sequence alignments for each of the monomers. How do we pick which of these we use in combination with each other? And it's not always going to be the top scoring MSA from each of them as a monomer. And then we have to do the actual sequence linking between the MSAs for chain A and for chain B and for chain C, where those are all unique chains. Now, there are two cases to consider. One is if you have a homo-oligomer, and in that case, both of these problems are really easy. We just make candidate structures with each of the multiple sequence alignments that we have for that single chain sequence. We go based on the predicted TM scores to score them. Good to go. Don't have to worry about the linking or anything like that. In the case of the heteromers, though, then we have this potentially combinatorial problem where we've got up to 10 candidate sequences for each of our monomers, up to 10 candidate MSAs for each of our monomers, and then we have to figure out how to put them together. So what we end up doing is evaluating no more than 100 of these. So if we have M separate monomeric sequences, then we pick N, the number of candidate MSAs that we will consider, such that N to the M power is no greater than 100. And then we'll do all the possible combinations of the multiple sequence alignments for the individual monomers at that point. And then we just get into the folding. And at this point, it really is just we plug each of the candidate MSA pairings out of the set that I just talked about into AlphaFold 2 multimer. Right now, we are still just letting AlphaFold 2 multimer do its own internal sequence linking across the different MSAs. I think this is an area for future improvement, something we're working on, but not done with yet. We generate we sample 25 models for each of our candidate MSA pairings, and then we will rank them based on the predicted TM scores. So these are the methods, and at this point, I will hand it off to Wei, and he will be able to talk about the results that we've obtained in CASP15. So we need to switch to Wei's screen and get his audio.
Thank you. So I may need the permission to share the screen.
They're indicating you should be able to now.
Yes, you have some issue.
Just one moment, sorry. You can try now.
Okay, thank you.
There we go.
Can you see my screen?
It's we got some pretty epic wallpaper. There we go. It's up.
Okay.
Yeah, it's all good. You can go ahead.
Thank you for the invitation from CASP organizers. I will introduce the results section for UMTBM server and the Zheng human group. As we mentioned, UMTBM server is built on the ITESR algorithm, which is an extension of our previous ITESR algorithm. This slide summarizes the folding ability of ITESR series algorithm for FM targets from CASP11 to CASP15. ITESR, which is a pure fragment assembly-based method, took in part CASP11 and only for one FM target. In CASP12 and CASP13, two versions of ITESR algorithm, which using the DCA-based contact and deep learning-based contact to get the ITESR folding simulation, shows better folding ability. Whereas the ITESR fold around 50% of the FM targets in CASP13. After deep learning predict distance is introduced, the ITESR in CASP14 generates model with an average TM score around 0.6. This time, the new version the ITESR algorithm that interpolates distance predicted from AlphaFold2, attention potential, and deep potential could generate further better model with an average TM score increase around 30%. Although the results show the ITESR folding system could become better by interpolating more state-of-the-art deep learning method. Since the new version the ITESR algorithm integrated the AlphaFold2 as its component for predicting distance, it's important to check the ITESR folding performance against the standard version AlphaFold2. This figure shows the head-to-head comparison of the TM score between those two methods. The AlphaFold2 model are taken from the CASP standard AlphaFold2 server. Overall, the ITESR performed better in FM targets. As a proof, over 80% of the FM targets that the ITESR generates significantly better model than AlphaFold2. Here we highlight 3 FM domains and 1 TBM domain that came from a same target. For all those domains, the tester outperformed AlphaFold2. We want to investigate why the tester performed better than AlphaFold2. We know the tester is a method that combines MSA, threading template, and deep learning based distance folding simulation with a comprehensive tester force field. Here we saw this slide to check which components leads to the success of the tester. This figure compares the folding performance of the tester with 3 different versions of AlphaFold2. Overall, AlphaFold2 using our Lomé3 templates is slightly better than the standard version of AlphaFold2. Furthermore, after giving the AlphaFold2 our DeepMSA2 MSAs, it can generate a much better set of models. The models of the AlphaFold2 with Lomé3 templates and DeepMSA2 MSA will be used as the initial confirmation for the tester simulation, which means the Lomé3 templates and DeepMSA2 MSA indeed contribute to the final model of the tester. As we can see, there is a gap between the third bar and the fourth bar. Thus, the improvement could be considered as the contribution of the tester folding system that combine multi-source distance from different predictors. Here we use one case of T1125D2 to highlight the advance of the tester in combining multi-source distance for the protein folding simulation. T1125D2 is the second domain of target T1125, where the tester correctly predicts the domain boundary. If we check the distance map of this domain from the whole chain level distance map, we can find that the error of the predicted distance is 0.53 angstrom. However, due to the domain level MSA contains more homologous sequence, the domain level distance map has a relative lower predicted distance error. Furthermore, the DI tester folding simulation has the ability combines the whole chain distance map and the domain level distance map, resulting in an even slightly better distance map with an error of distance around 0.48 angstrom. Guided by this combined distance map, after the tester folding simulation, we got an accurate final model with TM score of 0.83. Modeling large multiple domain targets is more difficult than modeling a single domain protein in many years. However, by checking the multiple domain and single domain targets this time, we found the tester has comparable modeling ability for those two kinds of proteins. Despite the overall performance is good, we still notice the tester failed in generating high-quality models, especially for some multiple domain proteins. For example, T1154D2, we over-predict it as 2 parts. Although the 2 parts will have a very good quality with GTTTS score all greater than 0.8, the entire domain model has a relative low GTTTS score of 0.75. This is mainly because the combined distance map of those 2 parts break the orientation between them. We have shown the results for UMTBM server. Next, we will focus on the results analysis of Zheng human group built on the DeepMSA fold multimer for protein complex modeling. In the following talk, we will short the word DeepMSA fold multimer as DeepMSA fold and AlphaFold2 multimer as AlphaFold2. Again, we compared our method with the standard AlphaFold2 in either global fold reflected by the TM score and the interface modeling quality reflected by the interchain contact FN score. Overall, DeepMSA fold could generate models with better quality in both global fold and complex interface than AlphaFold2. Since DeepMSA fold mainly focused on optimizing the input MSA given to AlphaFold2, And our MSA has two major differences from the AlphaFold 2 MSA. One is the MSA generating, ranking, and pairing system, as mentioned by Peter. And the other is we using a huge in-house metagenome database to construct the MSA. Thus, it's important to check whether those two things work for the CASP15 targets. As we see this figure, the first bar and the second bar in here, when giving the deep MSA fold same set of database as AlphaFold 2. For example, give them the genome and the BFD metagenome and Magnify metagenome. Deep MSA fold still can generate slightly better model. Furthermore, if we give the deep MSA fold our in-house metagenome database, the model quality is significantly improved. Thus, we believe both the large-scale in-house metagenome database and the MSA generating ranking pairing system are the key factor to the success of our method. Here are three nanobody and gene complexes that AlphaFold 2 can generate models with TM score lower than 0.7. However, deep MSA fold can generate very high quality model with TM score all greater than 0.9. Taking H1144 as an example, by checking all models created by deep MSA fold during CASP15 season, we found many of them actually had the better quality than AlphaFold default models. Furthermore, if we check the PTM score, it has the ability to correctly pick up one of those high quality model as the first model for Zheng human group. Interestingly, when we give the deep MSA fold the same database as AlphaFold 2, it still can generate very high quality model with TM score still greater than 0.9. Those results indicate the proper way of MSA generating, ranking, and pairing is critical for building correct model for the nanobody and gene complex. As we can see in the last slide, PTM score from AlphaFold 2 has the ability to distinguish high-quality models from the low-quality models. However, it still has some problem in ranking the high-quality models. For example, T1170, H1172, and H1171 are a couple of complexes that contains a heteromer, where H1171 is a A6B1 complex, and H1172 is a A6B2 complex. Deep MSA fold correctly predict the models for T1170 and H1171, but it has some difficulty to correct pick up the model for H1172. In experimental structure of H1172, the two copies of B proteins are in the neighboring positions. However, deep MSA fold actually predict this complex with 3 states, as shown in this figure. The wrong state model has been ranked as the first by Zheng group due to it has slightly better PTM score compared with the correct state by model 3. Okay, in summary, first we think what went wrong, we went right. The tensor that integrates threading templates, structural model ranked MSAs, deep learning based spatial restraints, and the folding system with comprehensive tensor force field works well for the protein monomer structure prediction. What's more, deep MSA2 with the high quality MSA generating, ranking, and pairing system helps improve the model quality for both protein monomer and protein complex. Second, what we think went wrong? AlphaFold QA score has the ability to distinguish model if they are significantly better, but it is still not sensitive enough to rank high quality models. Furthermore, we think domain partition is still meaningful and important for modeling large multiple domain targets. However, the accuracy of domain boundary prediction is still not good enough. Here, I need to thank Dr. Yang Zhang and the other members of Yang Zhang Lab for the help in methodology development. Also, very appreciate the CASP organizers provide the opportunity to let us share the protein structure prediction experience. Yeah, thank you for the attention. Thank you for your attention.
Thank you very much for sticking to the time limit. And we'll have time for a couple of questions. Arnie.
So I ask, my question is just, what is the compute cost for your pipeline compared to, relative to AlphaFold default? Is it like 10 or 100 or 1,000 times more?
Wait, you want to estimate?
Peter, do you want to answer or let me answer?
Actually, I can. So it's about right now. It's about 10 times more the way it's running right now for the monomer. But we think that we can make that a lot faster if we DI on the GPUs, which we have not yet done. So that's actually some of the compute time is actually doing that on Monte Carlo sampling. We're working on the GPU side of things, but it's not there yet. But that should be.
There was some other question. Yes.
I have a question regarding the first part of the presentation. Thank you very much. Do you also predict the orientations between the residues?
So the residue orientation, sorry, there we go. Oh, look, I can actually, okay. So the question is regarding methodology, do we predict the orientation between the residues? And explicitly no, but that is getting captured in all of these geometric restraints that are showing up.
Okay, and do you do something specific with respect to the rotameric states of the